Hello and welcome to the very last part of this series. To start out, we're going to talk a little bit about what we want TNT to be like. First of all, we definitely want it to be consistent, which means that it contains no contradictions. You'll remember that this is just a propositional calculus, this isn't TNT, but we'll remember from the rules that we can substitute any sort of well-formed TNT string for the letters P and Q, and we'll still get the same result. So you see, this is exactly the type of contradiction that we're going to be worried about. We don't want something and its negation. So if we can find any contradiction within TNT, it means that every single well-formed string is going to turn out to be a theorem. Then we also want it to be complete, which just means that everything is represented. So out of those goals, how far have we actually come? Is it consistent? Well, we don't have a proof for that, but it at least seems like we're not going to find any contradictions, so we'll just say it's probably consistent for now and leave it at that. And as far as being complete, we know for sure from last time that everything primitive recursive is going to be represented, so we've got that. There's also a lot of other stuff that isn't primitive recursive, but we also know for sure that it is represented, but we don't really need to talk about any of those things. And then there's a lot of other things that, again, we're not going to really talk about. We don't have any way to say for sure that they're represented, but it seems like they probably are. And perhaps thankfully for some of you, we're going to take a little break from working with TNT and we're just going to talk about stuff that sentences can do. For our purposes, we're going to keep the sentences very simple. So we have here a average, everyday sort of sentence. But there's nothing wrong with talking about sentences in a sentence. We can certainly imagine a sentence that has 5 words, but the sentence itself doesn't contain what sentence it is talking about. But then, there's nothing wrong with actually including the sentence that it's talking about within the sentence. And we don't need to think about the meaning of this sentence, all bachelors are not married. We just need to think about how many words it has. Then there's the sort of sentence that doesn't contain the sentence that it's talking about, but it does contain instructions on how to make sense of it. So we're not talking about rats, we're talking about some property of the word rats. So once we take out the instruction, and once we flip the letters backwards, we're left with the sentence, a star is only visible at night, which makes perfect sense. From here on out, we're going to talk about a very specific instruction. So if you do this to our first sentence, you just get, this apple is big, in quotation marks, and then you say, this apple is big. Makes no sense at all, it's not a sentence. So the only way to quine something that results in a complete sentence is to take a subjectless sentence fragment, and then quine that. Most subjectless sentence fragments result in kind of silly things when you quine them, but that's fine. And the less silly way to make stuff out of quining, just start with a subjectless sentence fragment that is talking about properties of subjectless sentence fragments. Certainly we can tell whether a subjectless sentence fragment begins or does not begin in a capital letter. In this case, it's even a true sentence, since we look at the first letter, it's not a capital letter, and what we're claiming about this thing that we're mentioning in the quotation marks is that it doesn't begin with a capital letter. So that's true. If we take the sentence, with vowels omitted doesn't result in any words, with vowels omitted doesn't result in any words, clearly that's referring to some other series of letters. What series of letters is that? Well, it's this one. So, we've got something in quotation marks. Oh, and the instructions are to quine whatever happens to be within those quotation marks. So what is it that we're going to be quining? Look, that's a subjectless sentence fragment. We've got has 3 words, has 3 words. We can see that that's true. Now, what was A making a claim about B? Oh, it's just saying that whatever B is going to be a full sentence. Is B a full sentence? Yes, it's even a true full sentence. That's nice. Oh, so we're going to quine whatever it happens to be in those quotation marks. And again, we're making a claim that it results in a full sentence. Now, what is it that we're going to quine? Oh, we're going to quine this. Let's see what happens when we do quine it. Is this a full sentence? Yes, it is, so statement A happens to be true. But the strange thing is, sentence A and sentence B just happen to be perfectly identical. Since I don't think we've done anything too difficult, I think you can figure out yourself that When you quine a subjectless sentence fragment that talks about quining itself, then we're going to have the sentence and the sentence it's referring to end up being identical, which means that sentence A is really making a claim about itself, since the sentence that it's referring to is identical. So this sentence A here is really just saying this sentence is a full sentence in a fairly complicated roundabout way. And this is the point we really want to take back to talking about properties of TNT. We're going to be doing something that we'll call arithmoquining. So you've got to start with a number. Step 1 is to call that number A. Step 2 is you look at the number, and whenever 262 appears within that number, you'll take it out and replace it with this. You're going to do a lot of copies of 123. In fact, you'll do A copies. And then once you've done that, you'll tag a 666 at the end. We'll call 378,262,501 as our number A. But anyway, let's do the arithmoquining. So, 378, that's what we started with. We're going to keep it there. Next we had our 262, which we know we're going to take out. We're going to put a whole bunch of copies of 123 in right there. And then we're going to finish with a 666 after that. So we've got 123, and we're going to do that 378,262,501 times. But once we get to the end of that, we're going to put the 666 and then the 501 at the end. There's just one more rule. If, after the 262, you have a 163, you don't do anything to the 262, you leave it just how it is. Now, we're going to take a number that we know is going to be our numeral interpretation of TNT. 262, in fact, stands for the symbol A. 111 stands for the symbol equals. 123 stands for the symbol S. And 666 stands for the symbol 0. So the TNT sentence that this corresponds to is A equals 3. Or for the moment, we're just going to treat this as an ordinary number, since it is an ordinary number in addition to being something we can interpret as TNT. We're going to call this number A, and then we're going to arithmoquine it. Obviously, this one starts out with the 262. There's no 163 after it, so we're going to take it out, put a whole bunch of 123s followed by a 666 there. And yes, there's going to be A copies of 123, so this number is rather ridiculously long. So all the 123s, the 666, and then from there on, there's no more 262s, so we are just going to leave the rest as is and put it on the end. And you'll notice that there's nothing in this number that we can't interpret as TNT. All of these 123s followed by 666 is the same thing as a whole bunch of S's, followed by a 0. So what we're saying is this gigantic number is equal to 3. But even if it's false, if we start with something that is TNT, we're going to end with something that is TNT. In fact, from now on, we're not going to worry about arithmoquining numbers other than ones that also have TNT interpretations. And you'll notice that what arithmoquining does when there is in fact a TNT interpretation is just a specific type of substitution that we talked about last time. Namely, every time this A appears, since A is the same as 262 when we translate it into different symbols, which are numbers. If we plug it into our substitution notation that we were talking about last time, the number we have to use is this many S's. Put that in for A. And then what was A prime? Well, that is what number we want to substitute in for the A's here. What we're really asking is what number do we want to put in place of all the 262s? And the number we're looking for is how many copies of 123, which in this case is this number. We already figured out what we're putting in place of A, and then for A prime, we're going to put in the number of 123s we wanted, which turns out to be the exact same thing as what we were using for A. And since A and A prime are always going to be the same number, we're going to just say arithmoquine instead of substitution. And all this is when we use the same number for a and a prime in a substitution, we only want to write it out once because it's rather annoying. What we've got so far is this, which we'll remember is just a string of TNT that claims that two numbers have a certain property. In this case, it's that this number. Then we're claiming that a prime is going to be what happens when you take out the 262, replace it with this many 1, 2, 3s followed by a 666, and then leave everything else as it is. We can certainly imagine exactly what a prime is, and it's important to note that there's going to be exactly one value for a prime that's going to be true for this. We'll call this number u, since we don't want to write it out any more than absolutely necessary. So we know that this happens to be true, a and a prime, when you substitute this value for a and this value for a prime, in fact do have that relationship. And since arithmoquining is just a type of substitution, and we know that substitution is primitive recursive, we know that this is in fact going to be a theorem. So let's try arithmoquining some different formulas. The one that asserts that a free variable a is a prime number, and of course this formula has a way to write it as numbers. I don't want to write it again, so let's call it u from here on. So what we're saying here, if we put a whole bunch of s's followed by 0, if that number of s's is u, then we're saying that this number has a relationship with a prime, such that when we take all 262s that don't have a 163 after it, which happens to only be this one right here, we replace this 262 with this many copies of 123 followed by a 666. That's what a prime is going to be. So a is just the number way to write this, and if you were to take this 262, replace it with all the 123s with a 666 at the end, what would that be doing to the equivalent formula? Well, you'd take the a, replace it with a bunch of s's with a 0 at the end. How many s's do we want? We want this quantity of s's. We know for sure that the number that does satisfy this relationship for a prime is going to be some set of numbers that we can think of as TNT. And if we were to write in TNT, it would be this. So I hope you can see that anytime we use any number for a, where the number is the way to talk about this string of TNT, the number a prime that works for this is going to be one way to express this string of TNT. This is our shorthand way of writing some very long string of TNT. All strings of TNT that exist have a Gödel number, or just a way to write the symbols down using those numbers that we decided instead of the symbols. And we'll call whatever number that is u. And if it's a number, we can put u s's in front of a 0 and put it within this formula. Using this for a, there's going to be one number a prime that satisfies this relationship that we're claiming. And just like it was with prime, the number we're using for a is going to be one way of writing this, and then the way to write a prime is what we get is when we put in u for a. Absolutely no different than it was here. A prime here is just the number way to express this formula. And since this is exactly the same as this, a prime is the number form of this formula. I'm gonna guess that this is a lot to process. If you want to take a break here, come back later, be my guest. Now, we're going to take something that includes this ridiculous thing that we just found and add something else to the beginning. We remembered twin primes were fairly simple, so there's a number a double prime that's 2 smaller than a prime, they're both prime numbers, and that the a prime from here is also the same number that you get from arithmoquining some other number a. So what are we kind of saying? If you take some number a and arithmoquine it, which is a very simple process, the number you get, a prime, is not the larger number, in a set of two twin primes. Then this formula's Gödel number we'll call u, as we've been doing. Let's use u as the number that we are going to start out with. So we take this number, u, then arithmequine it. That arithmequanification, it's not the larger number of two twin primes. And since this is the weird mind-blowing thing where a prime has to be this formula's Gödel number, what we are saying is that this formula's Gödel number is not the larger number in a set of twin primes. Not only can you make a formula of TNT, which in an indirect but necessary way talks about its own Gödel number, but you can then also make claims about that Gödel number. Remember that this looks exactly like our last example, except that instead of saying twin prime, we're saying proof pair. So we start with some number a, arithmequine it to get a prime, then we're making a claim about that a prime, which is that there exists no a double prime that forms the first number of a proof pair. So you take that formula's Gödel number, we'll call it u, and you put it in as the starting number. To make sure you've been following along, I'm going to ask that you interpret this one yourself. Of course, don't worry if you think that's going to be beyond you, I'm going to explain it afterwards anyway. So go ahead and pause, and I'll give you my interpretation once you get back. Are you ready yet? Okay. So, we've learned that by using this method with arithmequining, we know that the only number that works for a prime is this statement's own Gödel number. So, we know this statement's own Gödel number does not have the first number of any proof pair. Is anyone seeing anything interesting about this yet? Because as it turns out, this right here is Gödel's incompleteness theorem. And that relies on two things, one of which we've already seen how it by itself can be quite mind-blowing. The way we've set up arithmequining so that if you substitute u gotten from here for the first number, we have a way of talking about a statement's own Gödel number. So think about it. What is the first number of a proof pair? It's just every single step in a proof that leads up to proving whatever this is as a theorem. So if this statement's own Gödel number does not have a proof, that means it is certainly not a theorem, which means that a perfectly valid interpretation of this statement is not a theorem. If you think about this in terms of whether TNT is complete or not, you certainly run yourself into a contradiction. If it's true and there's not a proof pair, that means it is both not a theorem and it is true. So that's no good. That means that TNT is incomplete because we've got a true statement right here that we know is not a theorem. But then if there is a proof, even worse, it means that TNT is inconsistent. If there is a proof, we could take that proof's Gödel number, put it in for a double prime, so we would have this statement without the tilde. There exists an a double prime because we found exactly what that a double prime is. And this statement would be a theorem. And since this statement is what we proved, anything with a proof is a theorem. So we would have there doesn't exist a value for a prime, and there does exist a value for a prime because we found what value that is. And since we have both a statement and its negation, then it follows that every single well-formed formula of TNT is a theorem. And at that point we can pretty much give up. But we're gonna assume that there's probably no proof, which is the only other option. Either there is a proof or there isn't. And even under those circumstances, TNT is incomplete. Because if there is no proof, then this statement is true. There's no proof pair either. Where either way we can't win. But maybe there could just be a better system? But any system, as long as it's good enough to talk about relationships between numbers, is going to be able to talk about proof pairs and it's going to be able to talk about arithmoquining. The only other option is for it to not be good enough at talking about properties and relations of numbers. If it's not good enough to do these things, then certainly it's not even very useful because there are properties and relationships of numbers that it can't talk about in the first place. So any system of number theory is either not going to be very useful or it's going to contain this. So this very statement is basically the end of the hopes that we can find a consistent and complete formalization of number theory. That's all there is to that. So let me know what you think. And I hope I conveyed the extremely interestingness of this whole thing. It's been a pleasure to have you. Thanks for watching.